Okay. So, now welcome to lecture number 2. So, we start from here. What did we learn in the first lecture? I gave you an idea about this Drude's theory. This Drude's theory, elegant theory in its time, more than 100 years ago, when Drude proposed this theory. It is really elegant theory. It is really remarkable that he the kind of assumptions he made, and then the kind of predictions which could be made appeared that this Drude's theory seemed to work, except that it was a good fortune that there was any matching with experimental results with Drude's theory, just because two errors cancelled out. Then I have gone on to show that if you do not have those two errors cancelling out, then in cases of Hall effect or magnetoresistance, and also for example this plasma frequencies for transparency of metals, and there are many other examples also where you see that Drude theory seems to work well for group 1 elements such as lithium, potassium, cesium, etc., but it begins to fail well for many other metals and many other situations. So, clearly something is wrong with that theory. The first improvement came by what was done was that you see what Drude assumed based on kinetic theory of gases, that when an electron collides with an ion, it comes out with random velocities, and those velocities are taken through kinetic theory of gases, which means they follow Maxwell-Boltzmann distribution. Now, we know that electron follows Fermi direct distribution, not Maxwell-Boltzmann distribution. And therefore, first improvement which was made was by what is called as Sommerfeld's theory of metal, in which essentially he took Drude's model, but substituted in there a Fermi direct distribution for electron velocities, and then he applied that theory also, which gave some improvement. But there is an objection to it, that in otherwise what is a classical theory, Drude's theory, that is, how could you put a distribution which is whose nature is quantum mechanical. So, that was the second, which is an objection to this Sommerfeld theory also, which therefore I have done Drude's theory because of its historical importance. So, I will not take care of this, I will not cover this Sommerfeld theory in here, but move on to perfectly quantum mechanical theory based on first attempt we will make is through free electron theory. I assume that the students are familiar with quantum mechanics. So, what I will do in this lecture is do a very quick 2-minute, 5-minute review of quantum mechanics, the relevant portion for free electron theory, just to jog your memory, but I expect you to know already. And then I will introduce this idea of free electron theory, and then in that free electron theory we will see quantum states emerging, and we will try to understand the meaning of k vector, which is very important, because you will see that eventually when we derive properties of materials, we will derive them from an energy versus k type of curve, from which all the properties of these metals and semiconductors would be derived, and hence it is important to understand the meaning of k vector, which will emerge out of this free electron theory. And then we will start putting, since there is I am saying already k represents a quantum mechanical state, in this state we will start putting electrons which are there in the system. So, this is where we will end this lecture midway in the free electron theory, and then in third lecture we will continue over this. So, let us start with a quick review of quantum mechanics. Essentially what I will do is that just the basic thing, recall that we deal with this wave function psi, and I am using a notation where I put hat on top of all of them. This quantity contains all the relevant information about the electron. It is a function of position and of time. So, this is the wave function which contains all the information about electron. You can derive anything you want through this wave function. Then of course, then it says that for every corresponding to classical operator, there is a quantum mechanical operator. These operators, let me write it as OP, these operators are given here, that for position there is a classical operator R, corresponding quantum mechanical operator is R. So, if there is a function f, the classical variable is f, there is a quantum operator f. For example, a momentum, if there is a momentum is p in classical variable moment, then in case of there is a equivalent quantum operator in quantum mechanics, there is a operator rather than the variable. This quantum momentum operator is like here, and if there is a quantity called energy in classical variable, then there is a energy operator in here in quantum mechanics, meaning thereby if I take this operator, if we apply this operator onto this operator, whichever operator we are talking about here, operator is applied to this wave function which I have written down here, then it gives you a eigenvalue of this particular operator. So, if I apply momentum operator on this wave function, then it gives me momentum eigenvalues multiplied by this wave function itself. That is the basic idea of these operators in quantum mechanics, you will recall. So, what I will do here is that I will sort of derive, if you wish, derive Schrodinger's equation, SCHRODIN wave equation. Obviously, you can understand that I am writing it, derive in inverted commas. What that means is, obviously, you cannot derive, it is basically a postulate, but I will pretend to derive by saying that in classical you think of 1 over 2 m, that means the kinetic energy, this is the total kinetic energy plus the potential energy is equal to total energy. That is what you think of in a classical way. What I will do is, I will take this momentum operator, apply on the wave function to derive the this kinetic energy, the potential energy and the total energy. So, let us just use these operators which I have written down here. Here are the operators, all these operators which are written down. Let us use these operators and derive this Schrodinger equation, quote unquote derive the Schrodinger equation. So, the way we will write it is as same thing, I will take the momentum operator. So, this will become, and j indicates, by the way, this j, I use symbol j. What is j? J is equal to square root of minus 1. So, this is an imaginary quantity, some people use I. So, I am going to use j in this in here. So, that is what this j is. So, and j square of course is equal to minus 1. So, what I am going to write this as minus h square by 2 m, and remember, let us introduce another symbol, this h bar. I hope you are familiar with this meaning of h bar. H bar is equal to Planck constant divided by 2 pi. That is what is written as h bar. So, h bar 2 m and gradient square, I am just taking square of this, applied to this wave function psi of r comma t, this vector r comma t is what I have written here, plus this potential of position and time, if you wish, equal to this energy. Now, I am going to write as times psi, sorry, since this is the function here and the corresponding operator is this of r comma t. This is then equal to this energy. This energy I am now going to use the energy operator minus h bar by j del by del t of this wave function again. So, here is our Schrodinger's wave equation which we have just derived from a classical sense. You notice that essentially this operator then becomes the postulate. So, I assume that you already know quantum mechanics. This is just a quick review of what we intend to do here, and so then what I am going to do is I am going to assume separation of all variables. I will assume that it is possible to separate this wave function's spatial part and time dependent part. It is possible to separate them out. That means, write this as psi of position only. The difference in symbol is that I draw these hats here in case of when it is r comma t, but if it is only, this is a different symbol when I do not draw the hats here, and that is only function of position versus phi, which is of time dependent. I am assuming that it is possible, it may not always be possible, but I am assuming that it is possible that to write the wave function as two separate functions, one of position and one of time. If so, then we can substitute this into our Schrodinger equation which I just wrote down. So, in that case this becomes h square by 2 m times phi, which is time dependent and hence you need not take its and this is only a spatial derivative. So, only phi appears here plus v times phi equal to, and then of course, only the time dependent part we need to consider here by j, and phi comes out and del phi by del t. Now, we separate it down like this, divided by what you get, divided by this quantity, what you get is minus h square. This is exercise you would have seen in past also. Some point in time, if you do not recall today, then you need to brush up your whenever you were introduced to this. What do you notice? What you notice is this is only phi dependent, which is a position dependent. This is only phi r dependent, and this is time dependent, and yet they are equal, yet two sides, spatial part and the time dependent part are equal. That only means that they both must be equal to same constant. They must be both equal to same constant, and that constant is that constant we are taking as the energy, and therefore, because spatial part we are going to write minus h square by 2 m. Therefore, we are going to write this as 1 over phi plus v as equal to this energy E, implies in more common form as we see it 2 m gradient square of phi, which is of position only, plus v phi equal to energy times phi. This is a spatial part and time dependent part. Part of the wave function. Then likewise, since this quantity E, this energy should be equal to the same quantity here, in the same both quantities should be equal. Therefore, minus h by j, we will write this as y del phi by del t equal to, implies that we will write this as h by j del phi by del t is equal to, which is time dependent only. We will assume in fact, in doing so, maybe I have made a mistake. I go back a little bit. In order for this to be true, I have to make sure that this v is only function of position. So, I should remove this part and should be only function of position. Only then it will be true that this part is only spatially dependent. So, hence we will assume that. So, we will assume that time dependence is harmonic This implies that we will take phi to be e to power some constant times e to power j omega t. That means, rotating in time with the angular speed omega. You can clearly see, you can substitute this into this equation right here, and you will see that this is a solution to this equation. So, we are going to assume that whatever we do subsequently, what we will assume is we will solve for only the spatial part of phi, solve for only spatial part psi, and assume phi to be e to power to j omega t, implies then this whole wave function r comma t to be equal to phi of r times some constant times e to power j omega t, time dependence of this point, and this is the part we are going to solve, right. So, this is all that we are going to do in this class. We are going to focus only on this part. You assume that once we have calculated this part of the wave function, it is always possible to multiply this by e to power j omega t, and get the whole wave function. So, essentially that was a quick review of the quantum mechanics which we need to do here. These are the operators. We will require energy operators, we will require these different operators we will require. So, now let us move on to this free electron theory. What do we mean and what are we doing here? Essentially, like I said, this Drude's theory, in this Drude's theory, which was a classical theory, Sommerfeld theory, in which a distribution was put in, which was quantum mechanical, but otherwise a classical theory. Now, we are moving towards something which is purely quantum mechanical. We will keep it simple, we will keep it very simple, and we will use the similar assumptions like Drude did. For example, this called free electron, we will assume that it is free electron. When we say free electron, in the same sense as Drude did, we will assume this free electron here to mean as free electron and independent electron, meaning thereby they will neglect any interaction between electron and electron, and will neglect any interaction, any potential arising of electron and ions. That means, we will assume that in a metal the ion positive charges are well shielded by the valence electrons, and the inner shells of the electron, inner shells, and because of the screening, the valence electrons are very loosely bound to the ions, and since they are very loosely bound, we will ignore this interaction and we will say this interaction is nearly 0, and that is what is really meant by free electron. If so, then how would we solve for this problem of conductivity eventually? How would we think of conductivity in a material, in metals? If this is the situation in quantum mechanical sense, is essentially what we are going to attempt to do. Now, recall, so what we are going to do? We recall that h square by 2 m phi, we derived this as to be equal to, this is the Schrodinger equation, the special part of the Schrodinger equation what we had derived. The free electron theory implies, free electron theory essentially implies V is equal to 0. That means, all the potential is 0 because there are no interaction. We have ignored electron, which is a fair approximation, which is not too terrible. Those are systems where electron interactions are very important, but electron ion interactions are typically present in material, which you can't ignore. But in some metal, if it is possible to ignore them, in that case potential is totally 0. There is no interaction, and essentially free electron theory therefore is about solving this equation of position. Of course, let me write it again this time. It is about solving this Schrodinger equation with some boundary conditions. What boundary conditions? Now, when you can since if you have material, you can make sure you can confine the electron into the material. After all, do not allow this electron to leak out of this material, so that it stays in the material. That is one way, and that you can do by not letting the wave function leak out of this material. That is one way. But when you are, and that leads such a solution, if you try to solve it this way, then you will end up with standing waves in the material. Now, when we are interested in transport of energy, then it is much better to deal with running waves, and in order to obtain a solution which is a running wave like solution, just for that, not that the other solution is wrong, just that for convenience, if you want a running wave like solution, then it is possible to write what are called as cyclic boundary conditions. So, I will write down the cyclic boundary condition mathematically, because it is not, it can only be, I cannot draw it, it is I am going to do it in 3 dimension, but in 1 dimension I will show you what it means. So, I am going to write down this von Karman boundary conditions. What are these boundary conditions? I am going to think of free electron. So, imagine this free electron confined in a cuboid of edge length L and volume V. So, that means 1 by 3 power of volume is then the edge length. So, imagine that this electron is confined in all 3 directions in a imagine this is confined in a cube in that case phi we can write at position x plus L comma y comma z is same as phi of x comma y comma z. I am going to write phi of x comma y plus L y plus L comma z is equal to phi x comma y comma z, and similarly x comma y comma z plus L is equal to phi x comma y comma z. This is mathematically written down in 3 dimension. If you wish to see it in 1 dimension, you can think like this. If this is a starting point, and what in 1 dimension, let us consider that dimension 1 dimension to follow a circular path, a closed loop. Imagine this to be the starting point and imagine this to be the terminating point. So, imagine a wave function which goes something, maybe use a different pen here, let me see. So, we draw a closed loop and we use another color here and we say draw the wave function, then it goes something like this. Let us say the wave function is like this wave, so that it terminates like this. So, it is the starting point. Imagine this, that x equal to L is weaved back onto x. So, this is the starting point, let us say, and this is the finishing point, x plus L. L is the total length here, this is the length, L we are talking about, this is the we are going around this, and this is of length L. So, we are going around x, you start from x and go x plus L, the whole start from x, go around the length L, and you end up at the same point, and therefore, wave function is the same. Essentially, what it is saying is that what comes in from this boundary leaves from this boundary in case of running band, in case of this kind of boundary condition, come in, come out, the energy comes in, energy goes out. So, this point is considered basically collapsed onto the starting point, and this in order to write, one cannot draw that in 3 dimension. So, in the 3 dimension, therefore, we are writing it mathematically. So, these are the boundary conditions we will apply for this running wave like solution. So, if this is so, then notice without regard to this boundary condition, solution to this particular equation is of form, you can see that phi of k is symbol I am giving this, r is equal to 1 by square root v e to power j k dot r. This k is the wave number, and you can take this and substitute in there, substitute this into this equation which is right here, up here into this equation, you substitute this solution. You can substitute there and check whether this satisfies or not. If this, you will find that this solution will satisfy there with definition that k, of course, k vector is equal to k of x, x hat, let us write it, k of y, y hat, let us write this explicitly, and that this energy then in that case is h square by 2 m k dot k. This is this same k, k dot k, or equal to h square by 2 m k square. That is the energy. So, this is the solution, and this square root v basically appears for normalization. That is, you must make sure that should be 1. So, essentially, in order to make sure that this wave function is normalized, this square root of v is appearing there, that is about it, but the form of solution is this right here. So, let us use a different pen here now. So, this is the form of solution essentially, which you can substitute into this equation right here, into this equation you can substitute in there. So, these two together then constitute the solution to this particular equation which is trying to solve as the eigenvalue problem. Okay. Now, we are going to go and apply the boundary conditions in there and see how the quantization starts appearing in this. Except even before I do that, notice we have introduced now k, which clearly is this solution is a plane wave like solution. This is a plane wave like solution. So, if you look at this vector k, then you can see I had mentioned that k vector has a meaning. Obviously, it is a wave vector first of all. First of all, it is a wave vector, that is fairly obvious from the solution itself, but what else it means eventually we will see, and this is a very, and you can see that this k vector automatically has started becoming related to energy. It starts, it already starts, this k is related to energy. We will see that this k also has implication, it has some meaning to, it relates to the momentum also, and therefore, meaning of k becomes very important, which we will try to understand subsequently as we go along in here. So, let us apply the boundary conditions now. The boundary conditions. One of the boundary conditions is that, recall, let me repeat this again, let us apply this one, that x plus L comma y comma z is equal to phi x comma y comma z. Let us apply this. Okay. So, what we will do? Let us substitute that into the solution. So, we have 1 over square root of v, which is a solution here, e to power j, and we will write this k x times x plus L plus k y times y plus k z times z as being equal to 1 over square root of v, which is basically this wave function, which as you know was j k x plus x k y y plus k z z, k dot r basically, e to power, remember the solution is of form j k dot r. So, essentially that is what we are writing here, essentially that is what we are writing, the 1 over square root of v was our solution form. So, I am substituting in there. What does that imply? That implies that from these two equations implies e to power j k x L is equal to 1. That is what it means. This boundary condition means this, essentially is what is implied by this boundary condition. This forces that k x cannot be any value, but k x can only be 2 pi multiple of L n x, where n x is integer, where n x can only be integer. So, n x value can be essentially, now notice that my value of k x is, our value of k x is quantized. So, n x is a quantum number, in that sense k x is a quantum number. Since n x can only be integer, k can take only definite values, fixed values, and recall since k is related to energy. So, energy can therefore take only discrete values, essentially that is a common feature which you see in quantum mechanics. So, similarly, by same token, if I use the other two boundary conditions, you will find then 2 pi by L n y would become from the second boundary condition, and a third boundary condition will find k z is equal to 2 pi by L n z. These are the only allowed, of course, n y n z are all integers also. These are also integers. So, this is what we get out of this, that let's summarize one more time, that here is the wave function which satisfies the Schrodinger equation together with the eigen value of energy right here. Let us use another color. So, let us use, so here is the wave function which satisfies our Schrodinger equation, and correspondingly the eigen value of energy which is dependent on this quantity called k, this quantity k right here. And then if we move on, then we find that if you apply the boundary condition to it, then the k can only take definite values, and since k can take only definite values, then energy is also discrete. Therefore, also what do you see? So, therefore, we now have 3 quantum numbers n x, n y, n z, and loosely speaking we can think of 3 quantum numbers to be k x, k y, k z, along with then the fourth one, which is the spin of the electron. We can now think of, recall that when I had written the wave function as only that of spatial and time. In addition to that, we should also consider the spin state, which I have ignored. We can assume that spin state is plus half or minus half, up spin or down spin. So, 2 spins are possible. So, along with these 3 quantum numbers plus the spin quantum number, then completely describes my system. Now, these k values are discrete. Let us see what it means. Let us do some calculation. H bar is equal to 6.63 into 10 to power 10 to the 34 minus 34 joules second divided by 2 pi, which is equal to 1.055 into 10 to power minus 34 joules second, and mass of electron of course is 9.11 into 10 to power minus 31 kg. So, let us then therefore calculate this quantity h square, h bar square by 2 m as being, I have calculated this to be 6.11 into 10 to power minus 39 in appropriate units. And if we take L to be 0.01 meter, that means 1 centimeter. If we take the L to be that dimension, then 2 pi by L is 628 meter inverse, and then in that case, if we look at this remember 2 pi by L of some integer multiple. So, let us look at this quantity h square by 2 m 2 pi by L square. This quantity then becomes 2.41 into 10 to power minus 33 joules. Now, notice that as nx changes or nxy change and nz changes by integer, one integer, kx changes by this much amount. So, imagine if one state to be at nx equal to 0, and then in that case we will see the energy to be 0, k to be in x direction. Let's assume, let's make assumption. So, let's assume nx is equal to 0, ny equal to 0, and nz to be equal to 0, and in next case let us assume nx to be equal to 1, ny to be 0, and nz to be 0. The next state, next accessible state for electron. So, if you look at this, for this case energy is equal to 0, as we are saying k square depends on k square, h square by 2 m, h square by 2 m, k square, that means energy is 0. In next case this k value will be equal to 2 pi by L. So, in this case nx is equal to 1. So, nx is equal to 1, that means kx will be equal to 2 pi by L. So, that is why I have done h square by 2 m 2 pi by L whole square. This gives me the idea of energy, next energy. So, here the energy will be 2.41, energy will be 2.41 into 10 to the power minus 33 joules. Now, this gap in terms of electron volts, you can divide this number by 1.6 into 10 to the power minus 19, only minus 19, and here is minus 33. So, that means in electron volts also the two energy levels, the one energy level and the next energy level is only separated by very small energy. So, it is always possible, though these energies are discrete, because this nx, ny and nz are all discrete, yet we can think them to be quasi continuous. So, we can think of quasi continuous energies, meaning thereby that as nx, ny, nz integers change, kx, ky, kz change by a very small amount. Therefore, the energies though discrete are changing by very small amount. So, it will appear that as if it is a quasi continuous energies. You can think that energies are almost continuous, though in principle they are discrete, as they should be in quantum mechanical system. So, let us go further. Now, what is the meaning? Vector k. One, of course, we know it is a wave vector, that we know. Second, what do we know? Momentum operator is, you will recall, this was the momentum operator. So, let us find the momentum eigenvalue. So, what happens? Let us do this. Therefore, we will take this operator and apply on the wave function. So, we will take this operator, apply on the wave function, and that should give me my momentum eigenvalue times wave function. Since I already know my wave function, so I substitute in there. What do we get? What we get is essentially you substitute in there, and you will get is therefore h k times phi as p phi implies this momentum as being equal to h bar k. Very interesting. What it says is that k vector is related to electron momentum. K vector is related to electron momentum. All right. What that means is that actually, but at this point in time I will also do a clarification that indeed in free electron k vector is exactly giving you electron momentum, but if it was not free electron theory, then in that case also, though not done here, k vector is related to the momentum in the sense that change of this quantity h k, this quantity h k, rate of change of this quantity h k is still gives you what is the external force, that if you apply an external electric field. So, that force, how does the electron respond, that to that force, change in this momentum is still the this still appears as momentum to an external force. What I mean is, if I have external force to an external force, the rate of change of this quantity h k is still affected by this electric field which is applied from outside, and hence we think of this also as crystal momentum. That means that it is not actually an electron momentum of the electrons if it is not free electron. In free electron case, this quantity h k is precisely momentum of the electron. In case it was not free electron, still h k behaves like momentum to the external force, though it is not actual momentum. This is another. Then third thing you can notice. So, essentially having defined the momentum and the crystal momentum, though in free electron theory I mention again that this is electron's momentum. Now, let us see what the dimensions of k are. K has dimension of reciprocal length. Belongs to reciprocal. I have written down this here that its dimension is reciprocal of length and belongs to reciprocal space. Its consequence we will see as we go along in this course. So, these are 3 points which you should remember. Now, so what do we have? We have states. So, let us look at occupation, next topic and last topic for this lecture. So, what have we derived? We have derived k x as equal to 2 pi by L n x, k y equal to 2 pi by L n y, k z equal to 2 pi by L n z. We have said that these are the 3 quantum numbers n x, n y, n z. These therefore define the k state. That means, they together define a k state k. They define a k state, and each k state can take 2 electrons, one spin up and one spin down. So, that means the 4 quantum numbers essentially kx, ky, kz, and the spin quantum number. That means I consider one combination of kx value, ky, kz value corresponding to one integer nx, ny, nz, unique integer nx, ny, and nz. Then that defines my k state, and in this k state I can put 2 electrons. So now I have defined what the states are. Now suppose in volume V, we have n electrons. And small n being equal to therefore capital N divided by V, which is number of electrons per unit volume. So I have n electrons in volume V. Question we ask is, how do we fill these electrons in these k states? Remember, nx, ny, nz can take any integer values up to infinity. In that sense, I have infinite number of k states, never ends, just continuously they corresponding to nx and ny different integers, the kx, ky, kz values. These are the states on which I can put electrons. On each of these states I can put 2 electrons. Question is, but I have only n electrons. So when I start putting n electrons on these k states, how far do I go? How far do I go in nx, ny, nz or kx, ky, kz, after which I run out of electrons? And therefore it will tell me what is the maximum energy those electrons can have and up to how far they go. Those are the issues we want to solve, we want to now address, though the states continue to exist ad nauseum, they just continue to exist. So now let us look at the filling part. So let us see, let us assume as example, let me show you example that assume nz is equal to 0, and if I draw this axis like this, this is kx, this is ky axis, then corresponding to nx equal to 0, ny 0, I have a kx, I have a state right here. So here we have a red, this is corresponding to nx equal to 0, therefore kx is equal to 0, corresponding to ny is equal to 0, therefore ky equal to 0, I have one point. Now corresponding to when nx is equal to 1 and ny continues to be 0, I will have another state right here corresponding to nx equal to 2, while ky is still 0, I will have another state here, and so on for nx equal to -1, nx equal to -2, nx equal to -2 for ky equal to 0. Similarly for ny equal to +1 and nx equal to 0, I have a state here, and so on. I will have all these states corresponding to, well, different combination of nx and ny's. I will have all these states which are I am denoting here. And what is the spacing between these states, between this and this? It is 2 pi by L, they are separated by 2 pi by L. And what is this spacing? 2 pi by L, of course. And you can see that even in 3 dimension, in 3D also, space between any two k states in any of the 3 directions, k directions is equal to 2 pi by L. Space between any 2 neighboring k states, in any of the 3 directions, whether kx direction, ky direction, kz direction, the spacing is between 2 pi. What does that mean? I can think like this, that what is the space, what is the volume associated with a k state. So this in 2 dimension I have shown as a square, each edge length being 2 pi by L. So now what I am going to do is I am going to write this as follows. Since the periodicity is 2 pi by L of all these points in all the in the 3 dimensions, then volume, and watch out the words here carefully, volume of k space, volume in k space, not real volume, volume in this k space. Here is the k space I have drawn, a kx, ky space consisting of kx, ky and kz. So any volume in that space is the volume of the k space. So volume of k space per k point. If you take one k point, then that obviously is just 2 pi by L whole cube. That is the volume associated with each k point, because the periodicity in k space is 2 pi by L. Okay. That implies that number of k points per unit volume of k space is just inverse of this, just I am writing inverse of this, that will be L cube divided by just inverse of this relationship which I have just written here. Inverse of this is L cube 8 pi cube, which is equal to volume V, real volume in the real space, 8 pi cube. So that is what this quantity is. Now, what have we done? We therefore now have density of k points in k space. We have a density, right. Once I have a density of points, then if I take large number of volume in the k space and sample over them, then all I have to do is basically multiply with this density. And anyway, as we go along, we will see what we are talking about. Now, what we are saying is, we are saying that if I take, notice that energy goes as h square by 2 m k square. So, all points of constant k have same energy. So, what surface, what if I think of this k space consisting of kx axis. So, if I think of kx axis, kx, ky and a kz axis. So, I think of a sphere in this, I think of a sphere in this about this point, and this has a constant k, some value k, and according to this value on this surface of the sphere, all points have same energy. Now, if I think that there are Avogadro, since I have to fill Avogadro number of electrons, n will be very large, Avogadro number, then if I am going to fill, that means I will be accessing almost 10 to the power 23 k states. If I am accessing k, that many k state, and I ask what is the radius of the sphere in which I am filling all the n. Since this number of sample space is so large, we can forget that this is a cuboid like arrangement. We can, once we have calculated this density right here in the k space, I can take any volume in k space, multiply that by this density, number of k points per unit k space volume. So, I can take the volume of the k space, multiply with this density, and what I can get is therefore number of k states in that volume. Essentially, that is why we have calculated this density in here. So, what I go do is now as follows. So, suppose these n electrons fill up to radius of this k sphere, which I just drawn here, kf, that is the radius of that sphere, then the volume of that sphere is of course 4 by 3 pi kf cube. Remember, volume in the k space, this is the volume in the k space, multiplied by V by 8 pi cube density of points in k points in k space, then that gives me total number of k points, then that gives me number of k points. And since each k point, so let's write this quantity as equal to, let us see, 1 by 6 pi square kf cube multiplied by V. That is what this quantity is. All right. Now, each of this, this is number of k points. Each k point can take up to 2 electrons. Therefore, 2 times number of k points, kf cube divided by 6 pi square multiplied V should therefore be equal to total number of electrons that I have. What that implies is that we can write n, which is equal to n divided by V, as being equal to kf cube by 3 pi square. So, my relationship, important relationship is Kf is radius of what we call as Fermi sphere. The sphere up to which the electrons fill. So, if I have n electrons per unit volume in a system, small n number of electrons per unit volume, then they fill up k states up to that radius Kf, and that is called the Fermi sphere. All right. Now, since we already know that energy depends on, since energy. So, now if you ask the question up to the whatever the Fermi sphere is, what is the energy? So, we know that this energy, Fermi energy, we will call as Fermi energy, will of course be equal to h square by 2 m Kf square. Just by same definition, Ef is Fermi energy. Is the highest energy which electrons have, because why? The Kf is the radius which is the largest radius. Since Kf is the largest radius, so the electron energy is highest there. All other electrons, imagine like this. So, I have a kx, ky, kz space, in that there is a sphere. In this sphere we start putting electrons. I start putting electrons at the lowest energy, I put 1 on each k state, I start putting 2, then we keep doing this, keep doing this, keep doing this, and we reach up to Kf sphere, where we put our last electron and they are done. All k states after that radius are therefore unoccupied. All electrons and all states below this Kf, up to Kf rather are all occupied, each having 2 electrons on them. So, what is the energy of the electron? Energy of electron is this Ef, and that energy is called the Fermi energy, and which now we can write as Ef, we can write also as substitute value of Kf in terms of n, just from this equation right here, take this equation and substitute in there. So, what you get is this comes out as h square by 2 m e 3 pi square n to power 2 by 3. So, now you know that if you take, remember, if we take a metal, if we take a metal, we know its density. You have seen in the first lecture. If we know its density, if we know its molecular weight, which we do, if we assume how many electrons per atom it conducts, then we can calculate what the value of n is. If we can calculate the value of n, then we can calculate the Fermi energy, energy up to which these electrons completely fill. That is one thing we can calculate. Second thing, what we can calculate, of that electron, that highest energy electron, momentum of highest energy electron at k equal to Kf. What is that quantity equal to? Of course, we know that momentum is hkf in this case, and that therefore will be h times, just substitute Kf in there. We know that what Kf is. So, 3 pi square n to power 1 by 3 in terms of n. So, if I know number of electrons, then I can predict what the momentum will be. Once I know the momentum, then I can divide it by mass. So, I can say what the velocity of this, highest velocity of these electrons is, which is h Kf divided by mass of electron, which then can be calculated as h bar by m e 3 pi square n to power 1 by 3. If you now, you remember what we did in root theory, we calculated estimate of velocity v 0 by classical equipartition of energy in context of in context of kinetic theory of gases, and we wrote that as 3 by 2 Boltzmann constant multiplied by temperature, and that we equated to half mv square, and we calculated velocity. Now, and we found that velocity to 10 to the power 7 per centimeter per second. Now, if you calculate this velocity, you will find that this Vf is on order of 10 to the power 8 centimeters per second, and at that time I had mentioned that we have underestimated velocity by an order of magnitude. That is what this is, that the quantum mechanics, the actual velocity is only 0.01. The Fermi velocity is almost 1%, within 1% of the velocity of light. So, that is why I will stop this lecture here. On free electron theory, we have built the basis. What we have done is that we have built the basis, defined what free electron is, then we have built the basis and we have calculated that we have k states, quantized k states, but very narrowly packed. So, therefore, you can almost think of them as quasi continuous. On these states, we start putting 2 electrons and we see how far can we fill this up, and we can fill this up to the energy what is called as Fermi sphere kF, and corresponding to that kF is Fermi energy, that is the highest energy electron can have. Corresponding to that, what is the momentum of the electron, what is the velocity of the electron, we have derived all those expressions and explained to you. Next time I will start with density of electron states, and then from that on I will give a quick view of how we can think of conduction in these terms. Thank you.